So basically, if we assume that the norm function, just to begin with, if we assume that that is defined to be equal to the sort of complex absolute value of the number, the complex number squared, z is equal to a plus b times omega, we can simplify this to something a bit more concrete. A function directly of just a and b is basically what we're getting. So we know that z is equal to a plus b times omega, and we can simplify that by substituting for omega and making z be complex and just representing it that way. So we can say it's equal to a plus b times, well, what is omega? It's negative 1/2 plus I root 3 over 2. And at that point, we can keep going. This is equal to a, and we can just distribute the b, so it's minus 1/2 times b plus b root 3 over 2 times I. So we can say that the real part of our complex number is a minus 1/2 b, and we can say that the imaginary part is b times root 3 over 2. And we can see by the definition of this absolute value function for a complex operand that if we square the absolute value, what we're really getting is the quantity of the real part squared plus the imaginary part squared. And so, for that reason, we can substitute into this equation here, we can substitute into, the magnitude or the magnitude of z squared, and we can say, well, n of z must be the real part of z squared plus the imaginary part of z squared. So in this case, we can keep going. We can just substitute a minus 1/2 b quantity squared plus b root 3 over 2 quantity squared. So this is a squared minus, well, we have 2 times 1/2 times ab plus 1/4 b squared, and then plus this next term, which is b squared times 3 over 4. And we can, of course, simplify that to say a squared minus ab, and then we get plus 1/4 b squared plus 3/4 b squared, and I'm sure you see where this is going. We can, of course, combine these last two terms and say we get our final answer of a squared minus ab plus b squared. And so that's very interesting, how we can derive that just based on a relatively simple idea of the magnitude of any complex number. And so from there, we can do a secondary proof that essentially shows that the norm of any Eisenstein integer can also be written as that Eisenstein integer times z bar, or z bar, where we can define z bar to be equal to a plus b times omega bar, where omega bar, or what I'm calling omega bar, is essentially equal to the complex conjugate of omega. So, and as many of you will recall, whenever we take a complex conjugate, we keep the real part constant, but we actually negate or take the opposite of the imaginary component of our complex number. So in this case, normally omega is simply -1 plus I root 3 over 2. Now in this case, we're actually taking the negative, or the reverse of the imaginary part. So hopefully you're understanding that we're going to have a negative there. We actually have minus I root 3 over 2. We're not actually changing any magnitudes. We're just simply reversing or negating the imaginary component. From here, it's mostly a matter of substitution, as I'm sure you can tell. We have these three sort of disparate equations for the different variables, so all we really need to do is substitute at this point. So let's do that, shall we? And what is z times z bar except a plus b times omega times the quantity, that whole quantity, times a plus b omega bar. So that's just substitution at that point. And of course we can simplify that to say, well, this is really a minus 1/2 b. As we've seen up here, whenever we have a plus b omega, we can substitute that into here, and we can get its, its, perhaps you could say, more basic or just sort of alternative representation as a complex number, a general complex number, and that is a minus 1/2 b plus I times b root 3 over 2. So, just again substituting that same thing. I don't want to waste too much time here. A minus 1/2 b, what did I say? Plus I root 3 over 2. That's that first whole quantity. And we're multiplying that by a minus 1/2 b. Derp. A minus 1/2 b. But this time it is minus bi root 3 over 2. And from here, it might seem a little bit tedious, but again, it is just algebra. It's well, I won't say it's algebra. It's very elementary distribution of variables. So really, what we get here, we can just take it term by term. So a times a, that's a squared. A times negative 1/2 b, that's minus 1/2 ab. And then a times negative bi root 3 over 2. Perhaps that's a mouthful to say, but it is simply 1/2 ab, and it's negative, of course, times I root 3. And then we go to the next set of terms, so negative 1/2 b a, so it's, again, minus 1/2 ab. Then the next two, it's negative 1/2 b times negative 1/2 b, so that's simply positive 1/4 b squared. A bit of a familiar term. And from there we can say it's negative 1/2 b times negative 1/2 bi root 3. So that's really plus 1/4 b squared I root 3. Correct me if I'm wrong. And then we can get these last three terms, which is bi root 3 over 2 times a. So in other words, we're just getting plus 1/2 abi root 3. And the next term is bi root 3 over 2 times negative 1/2 b. So from there we can say that's negative, or it's going to be a minus 1/4 b squared I root 3. And the very last term is a negative. It's going to be a negative after we distribute b squared times I squared times root 3 squared. And I think that's it. And so simplifying this a little bit, we can say, well, this is minus 1/2 abi root 3 plus 1/2 abi root 3. So those two terms cross off, as I've shown. And then we also have a plus 1/4 b squared I root 3 and a minus 1/4 b squared I root 3. So of course, it's the same idea. They cross off, thankfully. They cancel out. And, some of this might be looking a tad familiar, hopefully. If we have a minus 1/2 ab and a minus 1/2 ab, we can combine those two. I'll just underline them to show that. It's a squared minus, well, it's minus a half, so it's still just minus 1 ab. And then we have these two other terms. Let's consider those for a moment. 1 plus 1/4 b squared, and we also actually get minus 1/4 b squared. Now I squared is -1, by definition. It's the imaginary unit. So I squared equals -1. It makes this whole term be a minus, but of course we already have a minus there, so it's minus a negative, so we can actually change it to a plus, of course. And then root 3 squared, well, we can simply say that is 3. Now from there, you should be seeing the power of this, I suppose. Because really what we're getting is plus 1/4 b squared plus 3/4 b squared. And so, of course, it again adds up to a more elegant value of just a coefficient of 1. 1b squared. Thus we have shown, this derivation, along with the proof right above it that I've shown, sort of demonstrates that this value here, z times z bar, is equal to the norm of z. Because I've gone completely from this term here, z times z bar, just with a bunch of substitution and rewriting and canceling out in some elegant things right here. We've gotten to the exact same point that we were back up here. A squared minus ab plus b squared, and that's very interesting. So, anyways, sincerely, thank you all very much for watching. I think that's I suppose enough for one day, I think. And yeah, as always, feel free to comment or even subscribe if you don't mind. And I'll see you another time. Oh hey, that whiteout finally dried. Oh hey, that whiteout finally dried. What do you know?